Hello, everybody, and welcome to episode 2 of Technically Speaking. Really excited for today's episode. It gives me an opportunity to really geek out on a very technical topic. Psychrometry is something that I love to teach, I love to talk about, and it's such a critical part of what we do in water damage mitigation. So buckle your seatbelts. Today's going to be a pretty technical topic here in Technically Speaking. As we get started here, just a quick introduction. My name is Brandon Burton. I am your host for the Technically Speaking episodes, and I'm the Vice President of Technical Application here at NextGear and CoreLogic. I'm also the chair of the ANSI ICRC standards, and a lot of the information that I'm putting into the Technically episode series really comes from helping us understand and apply the ANSI ICRC S500. There's a lot of great information in these standards, and sometimes translating this really technical content into practical application in the field can be difficult, especially with the way our industry is becoming more and more technical. So today really strikes at the heart of that. This will be by far one of the most technical episodes that we're going to have in all of Technically Speaking as we dig deep into psychrometry. And I want to give you a little bit of a warning ahead of time that today's episode is going to assume a little bit of a basic understanding of psychrometrics as we go into this, but I will ensure that there is a good amount of review of the basics at the same time to make sure that we all can come at the technical topics in a way that we can walk away with some good practical application. So with that said, I did get a report there. There's a little bit of echo on the audio. I'd made a quick adjustment. So if somebody can post that for me in the question again, if there is any audio echo or delays, just post that as a question in the Q&A and I'll see that. So with that said, let's go ahead and roll right into it. So first, let me start with a little bit of an overview of what we're going to talk about today. Advanced psychrometry is something that really helps us understand how to balance a drying system and how to effectively expedite the way in which drying is going to occur within a project. And to get at the heart of that, I'm going to go through a couple of concepts today. We're going to talk about some concepts that for most of you will probably sound familiar at first, but then we're going to layer on what I call Psychrometrics 301, and we're going to take it a bit deeper down the rabbit hole, so to speak. That's going to help us ensure, again, that we can really maximize our drying rates within a project. And depending upon the complexity of a project and how built up assemblies are, the amount of moisture that we're dealing with, some of these concepts you'll use very often, and some of them are just tools that you want to have in the tool bag for when you really hit those difficult projects, or when you have a client that says the number one priority isn't cost, the number one priority is time. And sometimes that's the reality, is that time is more expensive than the mitigation process itself. And these tools can be really helpful in those circumstances. I also want to ensure that with all of these concepts, we keep in mind the principle of balancing the drying system, right? Drying is one side of the equation. Preventing further damages from that evaporating moisture is the other side of the equation. So it's really important that we not only talk about maximizing evaporation as we go through this, but controlling that evaporated water to ensure we're not just spreading the moisture around the environment. So with all of that said, let's dig into it and let's get into some of these concepts. So first of all, as a general overview, here are the concepts that we're going to talk about. We're going to talk about the HAT model. And hopefully that sounds familiar to you. If you've been through any form of a water technician training or something like that, then you've heard of the HAT concept. But we're going to take it, like I said, a bit deeper than we typically do. We're also going to go into some very specific terminology. You've hopefully heard of terms like relative humidity and humidity ratio or grains per pound. That's what I call Psychrometry 101. All right, we're going to go a bit deeper than that and go into some terms that we don't use as often, but are very important to understand in order to apply these principles. And then we're going to talk about some relationships between them, because at the end of the day, it is the relationship between these entities that causes drying to occur. So that's kind of gives you an overview. So let's talk about the HAT model first, and beginning with just kind of a basic overview of what we probably already know. First, HAT stands for humidity, airflow, and temperature. And the reason we use this model is to help us understand that in order to effectively dry a structure, we have to have a balance between all three of these entities, right? You can't have really good temperature and really good airflow, but completely forget about humidity. Obviously, we'll have problems if we do. So as a general review, what's important about each of these three? First, let's talk about humidity. In order for the drying to be effective, to have a good drying rate, humidity needs to be low, right? That's the really, really basic principle. And the reason for this is that your air has a certain ability based on the energy it contains. It has a certain ability to support water vapor. Think of it like a sponge, right? And if I take a sponge and I move that sponge to an area on a countertop where I'm trying to soak up a bunch of water on the counter, if that sponge is already saturated and full of moisture, then when I move that sponge across the counter, I'm not going to take on water. I'm probably going to deposit water, right? I'm just going to make the whole counter wet. It's a really good analogy for how humidity plays in the drying cycle. In more ways than one, and we'll get to some of those here in a moment. So lower humidities are important for the drying process to give us that ability to take on water from the surface. Air movement is important because that's what moves the sponge, right? And the reason I like the sponge analogy so much is because it helps us understand the purpose behind airflow. It doesn't really matter how dry air is. If the sponge doesn't come into contact with the moisture on the counter, it won't absorb any of that moisture. And that's the tool that is air movement. It places that sponge in contact with the target, right? We spent a lot of time on this in episode 1, and even in the pilot episode back in December, talking about how important it is to place air in contact with the wet evaporating surface. And in my opinion, it is the least understood aspect of drying. It's just how important that communication, that contact is between the two. But basically, that's what air movement does for us. And then we have temperature, something we're going to dig into pretty deeply today. Temperature is important because temperature it's the raw energy, the power that is going to cause evaporation to occur. Without temperature, we have virtually no evaporation. In fact, without temperature, we can have quite the opposite, because temperature truly is the engine that allows for that water that is in a material or in a puddle or on a surface to become a part of the gas that is above it. It's what creates the suspension. And we're going to dig really, really deep into that today. But before we leave that, let's talk a little bit about why it's so important to balance all three of these. Let's take, for example, that we have a drying environment where we have really good airflow. Air is moving across all the wet surfaces. We have a really good temperature. It's warm in the environment, but humidity is either unchecked or out of control. This is an environment where we're not exciting drying or mitigation, we're exciting damage, right? All we're really doing is transporting excess moisture throughout the environment. And instead of one area being wet and others being dry, everything will be wet and equilibrium will occur to the high humidity. The same can be said of any other combination of these three entities. If two of them are properly managed and one is not, problems are going to occur. For example, if we have a good low humidity and good airflow but no temperature, at the very best, we're going to have slow drying. In fact, we could have deposition of moisture on other surfaces, condensation at least. If we have good humidity and good temperature, but no airflow, believe it or not, we have an ideal environment for microbial growth. Now think about this for a moment. I can have a low humidity in my air mass several feet above the surface and a really good warm temperature. But if I have no airflow to sweep the evaporating moisture away from the surface, we end up with something called a high water activity. Moisture, as it evaporates, is going to create a layer at the surface that's very humid in a warm environment. And that's the humidity that really drives the scary damage. And that's where we get microbial growth. So it's important to understand, again, that all three of these need to be balanced. All three need to be in check in order for an effective drying environment to occur. So that's kind of the review. That's the basic concepts in psychometry that hopefully, to some degree, we all have a good understanding for, and the foundation that we're going to build on today. So given that foundation, let's move into the first kind of more advanced topic. Humidity, airflow, and temperature are typically represented as equal entities in the drying process. In reality, they are not. And to make things more complicated, the importance or the impact of each changes over time. And the reason this occurs is that throughout the drying process, it's a different job. right? What you have on day one, the characteristics of the water, the amount of water present, where it's located, where evaporation is occurring, all of this is dynamic and it's constantly changing throughout the job. In fact, if it's not changing, you've got problems, right? Because when we start initially, we're dealing with typically some amount of surface water, right? Initially, when we first initiate our drying systems, usually materials are wet to the touch. Hopefully you've done a good extraction. There's not puddles of water everywhere, but still when you touch that floor immediately after extraction, there's going to be a surface film of moisture present. And at that point in time, the most effective element in HAT is airflow, right? The only reason for humidity is to control that humidity. It's like drinking from a fire hose to prevent an excess humidity from causing secondary damage. And this is the reason why we generally set as a goal, just keep the relative humidity below 60% initially. Just keep it there so we don't get secondary damage. But we don't need an extremely low humidity initially. We just need tons and tons of airflow. In a future episode of Technically Speaking, we're going to dig real deeply into this airflow topic, by the way, and I'll share some very specific numbers about where you start with airflow and where you finish with airflow. And the most effective drying systems are those that start heavy and finish light. In fact, there are reasons why towards the tail end of the project, too much airflow is not a good thing. It can actually slow things down. But we'll dig into that into a future episode. For now, initially, air movement is critical up front. As we move into the middle stage of the drying process, things begin to change. Once surface water has been eliminated and all that remains is free water, air movement begins to lose its impact. So just in case you're not familiar with the term, let's discuss what free water is. Free water is a liquid water, just like surface water. It's a liquid, but it's not available at the surface. It's in the pores, the capillaries, the air gaps, and all the other spaces that live inside the material. It's the water in the sponge that if you were to wring the sponge would begin to fall out because it's inside of that material. So that's where things begin to change. Now the air movement is no longer touching the water directly, but because it's liquid water, evaporation rates will still be high. And because evaporation rates are still high, a good amount of airflow is still needed. What becomes more important at this point is a lower humidity and a slightly warmer temperature in the material. And you're going to hear me stress that a lot today, that where temperatures are important is not just in supporting water vapor in the air, but driving the evaporation process in the material itself. Then things really begin to change for the back half of the project. And if I were to put this in context, I would say that surface water is typically measured in minutes and hours. Free water is typically measured in a day or two at the most, and bound water is the rest of the process. This is the moisture that is not in a liquid form. This is the moisture that has been chemically bonded to the material that we're drying. It has a bond with the material itself. And this bound water requires energy to break that bond, to vaporize it, and then a low humidity to draw that moisture out. We'll dig real deeply into what those engines are and those mechanisms are today, because this is where, technically speaking, today, we're going to spend a lot of our time in Psychrometry 301, is understanding how to excite this phase. Because this is a phase that slows us down. This is the phase that typically takes the most amount of time. So with those concepts in mind, let's start digging into the real meat of the technical content today. In order to do this today, by the way, we're going to spend a lot of time on the psychrometric chart. If there is one action that I'm going to ask all of you to do at the conclusion of today's presentation is to start using a psychrometric chart more regularly. And I'm going to make this suggestion a couple of times, but in your inspection kit, on your desk, wherever you're working on a daily basis, have a copy of a psychrometric chart, laminate it, all right, and then grab a dry erase pen and start getting in the habit of actually using the psychrometric chart to understand what's happening on a drying project. When you're looking over those temperatures and humidities and what's happening or what happened, and you're trying to understand what was the opportunity or what should happen next, it's amazing what you'll understand if you start practicing putting a couple of lines on a psychrometric chart. And the more you do that, the more you're going to think in terms of psychrometry, and the easier the answers are going to be. All right. So having said that, I have a few terms on the slide right now that I'm not going to dig real deep into. I'm not going to dig real deep into the scale of wet bulb and dry bulb temperature, the scale of relative humidity, or the scale of humidity ratio. These are what I refer to as Psychrometry 101, right? The basics of psychrometry. Where we're going to dive in today is what I call the 301 end of the chart. The 301 end of the chart is way off on the right-hand side. And this is where we understand the relationship between heat, energy, and temperature, vapor pressure differentials, and dew point. That's where we're going to dig in real deeply today. And then we're going to take that information and distill that into some really practical ways that you can apply these on a daily basis as you're monitoring mitigation projects and making drying decisions. So with that, let's dig into first heat, energy, and temperature. So first, let's define what temperature is. Temperature is the measure of what we call sensible heat. Sensible meaning I can feel it, right? It's the heat that I can feel, the product of heat that I can feel. It's the intensity of the heat that is present, which can be measured or felt. So what the heck does that mean? To understand what that means, here's where you got to put on the seatbelts. We're going to get real technical. To understand what that means, we need to look at matter on an atomic and molecular level, all right? Bear with me for a second. Trust me, we're going somewhere with this. On the left-hand side of your screen, I want you to note the little figure of a water molecule, okay? H2O. This is one of the molecules that is present in air. There are several other molecules that are present in air as well. And I'm just going to represent a couple of them. We may have some carbon dioxide, maybe an oxygen molecule. If we wanted to get really technical, we'd throw some argon in here and a bunch of nitrogen. We throw a bunch of stuff in here. This is what air would look like if we represented it molecularly, okay? Air is going to have a certain amount of energy associated with it. That energy is a movement of these molecules. Now, here's what's important, okay? And I want you to just kind of work with me here for a second. I want you to imagine that dotted line going down the middle of my screen as a surface, all right? And this gas, this air is contained in this little area of my slide. Note how these molecules are impacting that surface. This is really, really important. That impact against that surface is going to displace a certain amount of energy onto that surface. The amount of energy depends on a couple of things. It depends on the mass, how much does it weigh, and it depends on its speed. When you take the mass and speed of an object and you make it impact another object, there's a name for that. We call that kinetic energy, all right? So to follow the analogy of what we mean by kinetic energy, I'm going to take you on a little mental field trip here for a second. I want you to imagine taking a table tennis ball, a little ping pong ball, and throwing that against the wall as hard as you can, all right? Because it's so light, even though it's going to be traveling at a high rate of speed, it's not going to impart much energy on that surface. You're probably not going to make a dent in the wall. Now I want you to take a cue ball, right, from a pool table and do the same thing. Throw it at the same speed. At the same speed, that cue ball is going to impart massive amounts of energy against that wall because it had a greater mass. Now take that understanding and again, look at the slide, all right? Notice that the smaller molecule is moving a lot faster. The bigger molecules are moving slower. Believe it or not, because of the difference in mass, they're both imparting the same amount of energy against that wall. That energy can be measured. We measure that as a temperature. So when you place your hand out into the air and you feel a certain temperature, it is the net effect of the kinetic energy of all the molecules that are in that air, okay? Really technical stuff. Hopefully that makes good sense now that we look at it this way, because it's huge in the world of drying. The implications of what we just discussed are massive. If I increase the energy associated with these molecules and start moving them around a little bit faster, all right, they impart more energy. When they impart more energy, that means we have an increase in temperature. Temperature is literally the sensible amount of heat, the intensity of that heat that we can measure and feel. And the more violently these molecules are moving, the more of them there are, and the more they weigh, the more mass they have, the higher the temperature. Okay, so that's what temperature is. Now let's translate this into a drying environment. So Brandon, what does that mean for drying, all right? Ground me in something here because I'm losing it. So on the bottom of the slide, we have a chain of water molecules. That chain of water molecules is liquid water. This is what liquid water would look like molecularly. Okay, it's a chain of molecules bonded together. In fact, it's a big pile of a bunch of chains bonded together. Notice how as these molecules are zipping around in the air above, they're impacting that chain of molecules. There are collisions that are occurring. And if those collisions are occurring with that surface, guess what's going to happen to these molecules in that chain? they're going to start taking on that energy. And the more violently and the more rapidly and the more massively these impacts occur, the more energy we're going to add to this chain. And the more energy we add to this chain, the higher its temperature. As that temperature increases in that chain, the temperature is its movement, right? It's that kinetic energy, the more likely these molecules are to break out of that chain and become a gas. So temperature is the driving force that begins to break these molecules apart. It gives them that energy so that we can break these chains apart and excite the evaporation process. All right. So that's temperature in a nutshell, and temperature's impact on the drying process. But temperature is commonly misunderstood as heat or energy. All right. And although they're similar, they're different. If you can remember from the first time you learned psychrometry, right, and that first time you realized the difference between relative humidity and grains per pound, for those of you that have been through any sort of psychrometric exercise before, and you had that aha moment where you finally realized, that's the difference between relative humidity and grains. Relative humidity is exactly that, right? It's a relative expression of the amount of moisture in air. It's relative to what that air could support or at saturation. And temperature is kind of the same thing. Temperature is relative. Temperature is relative to the total energy in a system, right? And how concentrated or intense that energy is. Let's understand what that means, because again, it's important. So heat and energy. Notice on this two sets of containers here, I have molecules on the left-hand side that have a certain amount of energy associated with them, right? A certain amount of movement, right? And in the container on the right-hand side, at the present at least, there's no movement at all. Well, nature always seeks an equilibrium. And as these molecules start adding energy to that dividing wall, that energy is going to become absorbed by the molecules on the opposing side. We're going to achieve what we call a thermodynamic equilibrium, where energy is going to flow from where we have more intense heat to where we have less intense heat. So in other words, temperature will always flow from the higher intensity to the lower intensity. And heat is a measure of that intensity. So therefore, temperature will always flow from high to low. So when you're in a grocery store and you walk up through the freezer section, right, and you're standing right in front of the frozen goods, and you feel that side of your body that is very, very cold, it's not because the cold is coming to you, it's because the heat in your body is going to it, right? That's the direction of flow. When you place your hand on a warm surface, right, the reason it feels warm is because the energy is flowing into your hand. It's high to low. That's the direction temperature will always flow. Now let's understand the difference between temperature and heat for a second. Heat is the movement of that energy between the two sides of the system. Energy, on the other hand, is the total content of that heat in the system. And to understand what I mean by that, I want to make a little change to this analogy. If we were to move that dividing wall all the way over here to the right-hand side, notice how we've compressed and concentrated the mass and the molecules over on the right-hand side. The amount of heat is now concentrated into a smaller space. And even though those molecules may not necessarily be moving as fast, believe it or not, the temperature now on this side is higher because we've concentrated the energy into a smaller space. Now heat's going to flow the opposite direction. All right. The only reason I shared that piece of it with you is to understand that there's a difference between energy and temperature. We'll talk a little bit more about why that difference is important to understand here in a moment. But for now, just hold that in your hat. Okay. Let's move on to the next topic here in concepts, in definitions. Now let's talk a little bit about vapor pressure. And then we're going to tie the two together, vapor pressure and heat and energy. First, let's define vapor pressure. Vapor pressure is the pressure of a vapor in contact with its liquid or solid form, literal definition. It can also be expressed simply as the force exerted by the vapor or the tendency of that material's desire or tendency to become a vapor. So what the heck does that mean? It basically means that anytime we've got a container like this and we've got a gas in that container is going to have a certain amount of pressure, right? So the vapor in it is going to exert a certain amount of pressure. That pressure is related to temperature. If I take a container, you can imagine this pretty easily, right? If I were to take a paint can and seal the lid on a paint can with a little bit of water inside the paint can, and then place that paint can on a stove. on a burner and start heating the liquid and gas inside of that paint can, the pressure in that can is going to begin to build. In fact, it can become so intense that at a particular point in time, eventually the can's going to explode, right? So by raising the temperature, we're raising the pressure. Why is that occurring? The reason it's occurring is because these molecules are starting to exert more pressure and force as they're moving more rapidly and violently within the space. In fact, if there's liquid in the bottom of the container, we're even adding more molecules to that gas because the liquid is evaporating. All of this starts to build the temperature within that container. Now, in addition to raising the temperature to raise the pressure, right, for a drying application, there's another component here that we need to understand. Imagine that the container is the building material that we're trying to dry, right? In order for something to move from one location to another, it's not just a high pressure in one location, it's also a low pressure in another location that drives that movement or drives that process. So we can actually measure that differential and understand which direction water vapor wants to move using vapor pressure. Let's take a look at it as a concept, and then we're going to make it practical here in just a second. So if this is getting a little deep and getting a little technical, don't worry, we're about to make it practical, okay? If we understand the difference between the pressure associated with the water in a material and the pressure associated with the air in contact with that material, we can determine which direction this water is going to move. Now, before we get into the practical behind this, think about this for just a second, all right? If you're on a drying project and you're looking at a building material that hasn't made progress for the last 2 days, and removing the material is just not an option, right? You need to restore this material. How valuable would it be to be able to take a measurement today that accurately and precisely determined whether or not the material will be drier tomorrow? How valuable would that be? Instead of reacting to lack of progress, right? You could forecast the progress. You would know that progress is going to be made and the driving force behind that progress. You could actually measure it. That's what vapor pressure differences can do for you in a mitigation project. So let's make it practical here and start understanding how you would do that. Now, again, the psychrometric chart, right? So I'm going to say it a few times today, but if there's one action that I really want to drive in today's episode, it's starting to make a habit out of looking at a psychrometric chart. A psychrometric chart it's like in the brain, it's like one of those muscles that gets really sore if you don't use it frequently, right? And the first couple of times, even today, when you look at this, it's going to make the brain hurt a little bit, but I promise you, if you practice this, it's going to become quite simple, all right? You've just got to practice it. Get the chart out, laminate it, use a dry erase marker, and just get comfortable with looking at a chart more frequently. But let's apply this. So let's say in our example, we have a material that we're trying to dry, and it's just not making great progress. In fact, it may even be wetter than it was the day before. The first step in this predictive measurement is to measure the temperature of that material. All right. And this can be done a couple of different ways. You can, spend $50 on a little laser thermometer and just measure the temperature that way. If you're using protometer instruments, I know they have in their MMS kit, they've got a little temperature sensor probe that comes with the MMS. If you've got, thermal imaging cameras, some of them are capable of taking point temperatures. So there's lots of different ways we could obtain the material temperature. So let's say in our case, this material that wasn't making progress, we measure the temperature and we obtain a measurement of 50 degrees. So we would go to our psychrometric chart, find the 50-degree mark in the bottom of the chart, and then highlight this little line here that represents 50 degrees, right? We would then need to measure the relative humidity associated with that material. Now, this requires a little bit of explanation. So a material, any hygroscopic material, the amount of moisture it contains will dictate the humidity that material creates in equilibrium. What does that mean? That means that if I place a thermal hygrometer on the surface of that material and contain it, a little piece of plastic over the top, right? Then the humidity underneath that little containment will equalize with the moisture in the material. And that relative humidity is specific to the amount of moisture in that material. It will not change unless the amount of moisture in the material changes. So measure the relative humidity associated with the material. You can also guess this, by the way. If you're dealing with wood, for example, and your moisture content in the wood is approximately 30%, the relative humidity will be 100%. And the reason that's true is because 30% moisture content is the saturation point for wood. So if the water is saturated, the humidity will be saturated. If you're at 15% moisture content, you're at half of saturation. The relative humidity will be approximately half of that, which would be about 50% relative humidity. Again, something we'll dig into a bit deeper in a future episode. So if that went over the head, don't worry about it too much. Measure the relative humidity at the surface. It may take 5 to 10 minutes to get an acclimation on a porous material. It could take longer on a non-porous material. But measure the relative humidity. Once you have that relative humidity, plot that on the chart. So here we see on our chart, we have a 50-degree temperature. We have a 50% relative humidity. Where these two intersect, all right, hopefully this is familiar, how to use a psychrometric chart here. If not, then I'm giving you all the answers on how to do it in the presentation here today. Move all the way to the far right-hand side. Go past grains per pound, which would have been like somewhere in the neighborhood of 26. Keep going, go past dew point, which we'll talk about in a moment, all the way to the far right-hand side, and we get the vapor pressure. Typically, the vapor pressure on your chart is going to be expressed in inches of mercury. That's usually the scale that's used. And what we see here is 0.18 inches of mercury. That's the force associated with the water vapor in the material. Its desire to leave that material as a vapor, right, to leave its absorbed state or its liquid state, is a force of 0.18 inches of mercury. Okay, so what does that mean? And it's not a whole lot of force. In order for any measurement, if you'll remember from episode 1, in order for any measurement to have any value, I need two, right? I need a point of comparison. The point of comparison we're missing here is the air. So let's add the air to the chart. And this is just a standard hygrometer reading, right? Your temperature and relative humidity. We take that reading in the air and we find out that the air is 80 degrees, 40% relative humidity. Sounds like a pretty good drying condition, right? That should be drying the material for me. Well, when you look at the psychrometric chart, it ain't, and it's not going to. And the reason it's not going to is because the air has a vapor pressure of 0.42 inches, right? The air's vapor pressure is greater than the vapor pressure associated with the water. And if the air is pushing harder, water's not coming out, water is going in. Technically, in this environment, what's happening is a wetting cycle. This is not a drying cycle. This is a wetting cycle. If anything, the material is going to become slightly wetter in the next 24-hour period, not drier. There's actually more than one reason for that. When we get to dew point, we'll look at that also. But this is one of the ways that we can understand predictively what direction that material is going to go. So great, we just defined a problem, right? And as somebody used to always tell me, anybody can tell me a problem, give me a solution, right? What's the solution? Well, here's the secret, right? The industry secret for today's episode, one of two anyway. Here's how you fix it, all right? What you have to remember is something I said a moment ago. The relative humidity associated with the moisture in that material is constant. It will not change unless the amount of moisture in the material changes. So that 40 or 50% relative humidity rather that we measured for that material, that's not going to change. All right, it's going to stay the same. So let's take that relative humidity line, and instead of having 50 degrees Fahrenheit, right, let's change that to 90 degrees Fahrenheit. Let's take the material and warm the material. Remember, the relative humidity is not going to change. So now we get a new vapor pressure. The new vapor pressure is at 90 degrees and that same 50% relative. In other words, that new vapor pressure is 0.71 inches of mercury. Now, water is coming out of the material with a force of 0.71. The air is only pushing back at 0.42. Which direction is the water going to travel? The water is going to leave the material. Drying is going to occur. That'll be governed by permeance, which again, in a future episode, we'll dig into permeance as well. But the difference between these two of about 0.3 inches of mercury is your driving force. That's the force that's driving the evaporation process. What fixed it was understanding how warm we had to make the material for this to occur. Now, there's other potential solutions that we could make. The other solution I could have made is instead of raising the material's vapor pressure, we could have lowered the air's vapor pressure, right? So that's another solution that we could have applied. In fact, using this model, I could know precisely how dry to make the air in order to begin the drying process and look at outdoor air and other opportunities to get there as quickly as possible. All of that becomes an option when we practice using the chart. And that's really my main purpose in showing you this example today. It's not necessarily to get you using vapor pressure every single day. It's to get you to use the chart every single day, because the more you use the chart, the more these types of options become apparent to you, right? And the more you start to think in terms of psychrometry, because that's all a chart is. It's just a relationship between these psychrometric principles, okay? So now we have the correct direction, right? And where can we apply? There's lots of different places where we could apply this concept. So let's take a look at some examples and how we would do this. And I'll get practical with this. And I saw the question about the relative humidity of the material. So as I go through these examples, I'll talk about how you might take that reading in each of these locations. So here we just have a schematic. This schematic is showing a structure that is built over a crawl space. It's got a couple of rooms, some interior walls. We've got some cabinets over on the far right-hand side. We've got carpet in the room on the left. We've got hardwood floors in the room on the right. And we've got a water damage, right? We're trying to dry this environment. So how would I apply this in this environment? Let's start with this wall assembly all the way over here on the left. The reason I picked this wall assembly as an example is because think about, the variables that are in play with an exterior wall like this. You could have a nice, warm, drying environment, that 80 degrees at 40% relative humidity, right? A nice, warm, drying environment. But then an exterior temperature that's quite cool. So just because your drying environment has a warm temperature doesn't mean the wet materials in this wall assembly are also going to be warm, right? They may be cool. And just installing drying equipment inside the space may not guarantee a good drying condition for the wall plate, for the exterior sheeting, for wall cavity insulation, if for whatever reason we were trying to dry that, or even the wallboard for that example, especially if there are multiple layers of wallboard like drywall. Those are not necessarily going to be as warm as your drying environment. So how would I obtain these readings? Well, in a case like this, one of the easiest ways to get an equilibrium relative humidity reading or a material relative humidity reading is to insert the RH probe into the wall cavity. Right? You've already got a little containment in there that's already holding on to the air that's in contact with those materials. Let's take a relative humidity reading inside that wall cavity. And that's going to give me a good general approximation for how wet those building materials are, right? So I could simply take it that way. If I wanted to be more precise, then I would contain the hygrometer's sensing tip directly to the target material I'm trying to measure, right? Whether that be the wall board or anything else, and just use a small piece of plastic, painter's tape, contain the hygrometer probe directly to that surface, right? Any of those is going to give me a good approximation. And an approximation is all we need. It doesn't have to be absolutely precise, right? And again, you can guesstimate on this. If I know the materials are near saturation, just use 100% relative humidity, right? You don't have to measure it. If materials are saturated, they will create a relative humidity that is saturated, and saturated is 100%. So this would be a good location to use it. Another location may be down here on the flooring material. And for some of the same reasons, right? I may have plywood that is in contact with a crawl space, and the crawl space could be quite cool compared to my drying environment that is up above, especially if I've got multiple layers like a carpet and a pad over plywood that's insulating that warm drying air from the target decking material, right? Then that target decking material could be quite cool. And again, the measurement here for my material relative humidity is pretty simple, right? Disengage the carpet in a corner, put your thermal hygrometer right down there on the surface, contain it with some plastic, measure the relative humidity, or just use a moisture meter. And if your moisture meter says that you're at like 28, 29, 30% moisture content or higher, it's 100% relative humidity, because that's the saturation point for wood. Approximating is fine. You do the same thing over here for my hardwood floor, and I could measure the relative humidity associated with the materials that are beneath my hardwood. The easiest way to do this is to take your hardwood floor drying system, those nice little mats that we put over the surface that are drawing the air up from underneath, and measure the moisture that is leaving that dry force, right? Leaving that rescue mat system or whatever it is that you're doing, and understand the amount of moisture that is in that air. The only challenge with that is that that system is likely raising the temperature of that air, which would lower the relative humidity, right? So what you've got to do is measure how many grains per pound are leaving that system, then use a chart to calculate that at room temperature. And that will tell you what your relative humidity is. That may have kind of boggled the mind there a little bit, but that's okay. Practice with the chart, it'll make sense. And I'll show it to you as an example here in just a moment. The last location I want to highlight for doing this would be over here with the cabinetry. You've got multiple layers of building material that are insulating the wallboard material behind these cabinets from the room temperature. We're more likely to be closer to the exterior temperature than we are the interior temperature when we get back into these difficult materials to dry. And again, understanding the amount of moisture present, the temperature that is present, translating that to a vapor pressure will help us understand whether or not we're going to make any progress on these building materials. Now, the next question is, how do I fix it, right? If I observe the fact that my vapor pressures just aren't high enough with these target building materials, how do I fix that problem? And how do I excite the moisture so that we can actually begin the drying process? What this does is it helps me understand how important it is. I'm going to back up a couple of examples here. How important it is to get warm air inside this wall cavity. It can justify the use of that system to heat the air inside that wall cavity. Take the 80-degree air that's in my environment and an inter-air drying system and force that air into the wall cavity. It's not always necessary, but if I take this measurement and I determine that, hey, there's moisture in this cavity, I have a high humidity, it's got a low associated vapor pressure, therefore no drying will occur unless I put heated air into this cavity, excite the moisture in the materials by warming them, and drive the vapor pressure in the right direction. It gives me that justification, right? It gives me that reason to say, here's the reason why it was done in this particular location. If the problem's down here on the floor, it helps me understand how warm I need to make the crawl space that's underneath, right? I've got a cold temperature underneath. How warm do I need to make it? You know, what's my target temperature? Play with the psychrometric chart. Say, if I heat it to 50 degrees, does that work? If I heat it to 70 degrees, does that work? At what temperature are my vapor pressures now pointing in the right direction? How warm do I need to make this? So it gives me targets that I can use. I don't have to guess, right? I know precisely how warm I need to be to start moving my evaporation in the right direction. So that's vapor pressure and vapor pressure differential as a concept. The last concept I want to talk about is similar. In fact, you could use this concept to replace vapor pressure differential and just use dew point temperature to make the same analogy or the same comparison. So first, let's define dew point temperature. Dew point temperature rather is the temperature at which air becomes saturated with vapor. Okay, we commonly think of dew point temperature as the condensation that we see out on the grass or on our windshields in the morning when we get up after it's been cool overnight. That's typically what we think of as dew point temperature, and it's related to dew point. But what that means is actually that we've gone beyond dew point. In order for dew to occur, a surface had to be colder than dew point temperature. Let's understand why I say that. Again, let's take a look at the chart. Let's pretend for a moment that we have a condition in a drying environment that is 80 degrees Fahrenheit, right? So we go to our chart, we find 80 degrees on our chart. This whole line that I've highlighted here represents 80 degrees. And inside that environment, we have a 40% relative humidity. So again, we highlight the relative humidity line through the field of the chart. Where these two intersect, we can go all the way to the right, and we can find that there's a dew point. It's the middle scale there. There's a dew point of about 54 degrees, somewhere in that neighborhood, right? What does that mean? It means that the air will become saturated, 100% relative humidity, if I cool that air down to 54 degrees. It's like taking a cup, a measuring cup, that can hold 2 cups of water, right? That has 1 cup of water in it. And then squeezing that measuring cup by reducing its temperature until it becomes only a 1 cup measuring cup. Now the 1 cup of water fills it, right? If I squeeze that any further, then water is going to start pouring over the edge. If I go any lower than the dew point temperature in that analogy, I'm going to start losing water from the air. It's going to begin condensing. The chart shows us that relationship. So take a look at this chart. If instead of going to the right, let's go to the left. And as I go to the left, I want you to imagine that line, right, that we have here for our condition of 80 degrees and 40%, about 60 grains per pound of water. That is the measuring cup that is full, right? That's how much water is in my air. And that's not going to change. Unless I remove water from the air or add water to the air, that's not going to change. I've got about 60 grains of water per pound of air. As we move to the right on the psychrometric chart, or the left rather, as you begin cooling that air, slowly move your eyes across that dotted line and see what's happening as I drop from 80 degrees down to 75, down to 70, down to 65. As I'm dropping that temperature, it's no longer 40% relative humidity. The humidity is increasing, right? At approximately 75 degrees, we become 50% relative humidity, right? As you continue moving to the left on the chart, eventually we hit the saturation curve. That's the very edge of the chart on that side on the left. Where that dotted line starts to run off of the chart, we're in a zone here where we're going to begin losing moisture from the air. And that zone begins at, lo and behold, 54 degrees Fahrenheit. That is the same condition that we calculated over here on dew point, 54 degrees. So you don't even need this scale on the right-hand side. You could calculate dew point just by taking a look at the left-hand side, right? Where do I hit that saturation line? Now let's translate that into something that's practical. What does that mean? How do I use that? How do I apply that to my drying process? Here's how you apply it. If cooling the air below dew point creates condensation, right? If I do the opposite, I'm going to get the opposite result. It's the nice thing about physics, right? Nice thing about science. If I do the opposite, I'm going to get the opposite. So instead of getting degrees below dew point and getting degrees of what we would call condensation, let's go in the other direction and let's be above dew point. Let's get degrees of evaporation, the opposite of condensation. In other words, if I know my dew point temperature for my air that I'm using to dry is 54 degrees, and I have a building material that is warmer than 54 degrees, then there is going to be capacity for evaporation on that surface. And the warmer that material is above dew point, the more evaporation is possible. And there's a really simple rule of thumb for this. If vapor pressure, and using that vapor pressure analogy is too complex for you, then just hold on to this one rule of thumb. We want at least 20 degrees of evaporation. And 99 times out of 100, if this is true, drying is going to occur. And we calculate this again by knowing our dew point is 54 degrees. So my building materials must be 74 degrees in order for drying to occur, right? And we can get into all the weeds and details for why that's true and why that works and how that works. And I'll touch on some of those here in a second. But if there's just one simple principle that you would extract from this and say, how do I know this material that didn't dry yesterday is going to dry tomorrow? Measure its temperature, compare that to your air's dew point, and ensure that that building material temperature is 20 degrees above the dew point of your air. Okay, that's the amount of energy required to drive evaporation. Now, the reason this is true is because if you look at the psychrometric chart, when we have 20 degrees of evaporation, notice where the dotted line at 74 degrees, notice where that intersects my relative humidity lines at 60 grains per pound. And I think you can see my mouse on the screen, but right here you can see where these two intersect. That 50% relative humidity line is what intersects here. At 20 degrees of evaporation, the equilibrium point is a normal relative humidity. The equilibrium point is a normal moisture content. 50% relative humidity is an approximation of normal. So that 50% relative humidity, in other words, that 50% approximation of saturation is going to bring any abnormally wet building material back to a normal moisture level. Now, more than 20 degrees of evaporation would get me there faster, but I know a minimum of 20 is going to get me to my target. Okay, and that's the reason why that works. So two concepts there that we can apply in the field. Vapor pressure differentials, much more precise, much more accurate, actually articulates the driving force behind evaporation. In a future episode, we'll take that even deeper and talk about how we can use that with perm ratings and literally calculate evaporation rates using perm ratings. You can literally determine how much water will leave the material over a period of time if you take that vapor pressure differential and compound that with its permeance rate, which, by the way, permeance is just the amount of water moving through the material given the vapor pressure difference. So we can take that deeper with math, and we will in a future episode. But if you want to keep it simple, use your dew points, 20 degrees of evaporation. All right. So those are the concepts that I wanted to run through today. I know today was a very, very deep technical discussion, and technically speaking, a bit deeper than we're typically going to go with these episodes. But let me review the simple concepts and just distill this down to some of the things I want you to walk away with today. All right. So in review with technically speaking, first and foremost, I want I want you to walk away from this and understand that the chart is important, right? Get in the habit, if restorative drying, water damage mitigation, whatever you want to call it, if this is your career, right, and this is who you are as a working professional, you've got to understand the chart. And I don't care if you're a technician, if you're a project manager, if you're a water mitigation division manager, understand the chart, practice the chart, use the chart. Use the chart when you're watching the weather at night, right? Just use the chart and get comfortable with it. Laminate it, get a dry erase marker and start plotting readings on it. And I guarantee you that if you do that, it's like any other muscle that you practice in your body. If you do that, it'll become comfortable. And as it becomes comfortable, you're going to be capable of thinking in terms of psychrometry. And now, gloves are off at that point. The potential for what you can dry and how you can dry it and how you can manipulate that drying environment, potential is unlimited. Okay. The second thing I want you to walk away with from today's episode is understanding that transfer of heat, the energy, the excitement in the driving process, just like we talked about in episode 1, it happens in contact, right? It doesn't matter what the temperature and humidity of the air is above the surface. What matters is the temperature and humidity in contact, right? That's where the action happens, is the air that is in direct communication with the evaporating surface. So it all happens at the surface. The third thing I want you to walk away with is understanding that vapor pressure is what drives the drying process. And the more I can excite the vapor pressure in a building material, the more tendency there is for vapor to leave that material. The other side of that coin is the more I can lower the vapor pressure of the air, right? Because it's really the difference that does it. The more I can have moisture leaving that material. And then finally, last but not least, the final concept that we talked about today, 20 degrees of evaporation. That should be your target. Building materials that you're trying to dry should be 20 degrees above the dew point of the air they're in contact with. Right? Really important, especially when you're talking about exterior assemblies, especially when you're talking about cooler times of the year. Very important when you're talking about even things like concrete slabs, right? Very important that we've got that 20 degrees of evaporation. Okay, so with that, I'm going to go ahead and roll into just a couple of quick closing thoughts here, but stick around because we're going to do a Q&A session. I see lots of great questions over here on the side, so we're going to get into those here in a moment. But I do want to close up with just a couple quick thoughts. Again, my name is Brandon Burton. I'm the Vice President of Technical Application here at CoreLogic and NextGear and Chair of the ANSI and ICRC standards. And I will be your host for several episodes of Technically Speaking. I'm going to give you the program schedule here for the year. Today was episode 2, Advanced Atmospheric Readings, but take a look at what we've got coming up for you this year. Every month this year, we have another episode. The next 3, if you like psychrometry, we're going to dig really deep into some of the concepts we talk about today. It's not going to be quite as technically overwhelming because we're not going to have such a broad subject area, but we're going to kind of slice a bit deeper into some of the independent parts of humidity, airflow, and temperature. The next episode, by the way, is March 29th, 10 a.m. Pacific. Mark your calendars. And I will be here with you as we go into the next topic of balancing the drying environment. That'd be March 29th, 10 a.m. Pacific.